All right, we're going to talk about formal logic a little bit more today, and specifically, we're going to talk about compound statements. Okay, so remember from yesterday, a statement is a logic, has a meaning in logic that is to have a value of true or false without any other additional information being necessary. Okay, so today we're going to take statements and put them together. All right, a compound statement is just taking two statements, creating a new one using a connective, such as a connective term, such as and or. Okay, so first thing we're going to talk about, the first type is going to be with using the word and. It's called a conjunction. Using the connective word and to join two statements. That's what we mean by conjunction, is we're going to use and to join two statements. So for example, you might say something like, it rained today. And Sam plays tuba. Okay, so I've conjoined two statements together here. I have it rained today. Maybe we call that statement P. Okay, Sam plays tuba. Maybe we call that statement Q. All right, so we've named the two statements P and Q, and we're going to denote that with this upside down V. Kind of looks like an uppercase V, but upside down, all right? And so that means and. And so if we were to write this symbolically, we would write P and Q. Let's look at the truth table for P and Q here, all right? So let's see here. A little dotted line. And then let's set up a truth table. So we have P, Q, and then we also have P and Q. Okay, so let's look at the different combinations here. So we can have P be true and Q also be true. Right? That's one combination. Both statements could be true. If they're both true, then P and Q is also true. All right, so if it did rain today and Sam plays the tuba, then the whole statement, it rained today and Sam plays tuba, is also true. We could have true false. So we could have the first statement be true, the second one be false. But if one of them is false, then the whole statement is true. So if it rained today, but Sam doesn't play tuba, then the entire statement, it rained today and Sam plays tuba, is false. We could have the first statement be false and the second one be true. And if that was the case, then the entire statement would be false. And then the last possibility is false, false, and that means the whole statement is false. Okay, so if both of these parts are false, then the entire statement is false. So that's the truth table for P and Q. Let's go over to the next one. The next one is disjunction instead of conjunction. It's a disjunction, and that's where we use the connected word or to join two statements. Okay, so I might say something like, I rolled a 4 on a die, maybe, or burnt my toast. Okay, so that's our statement. And so if we break this up into the two parts here, I rolled a 4, that's P. Burnt my toast, that's Q. And then the or is going to be represented by this symbol here. It looks like a uppercase V. If you type it in a computer, it's going to look a little bit wider and taller than an uppercase V. But anyway, that's the statement for or. So you would write P or Q. That's how you would denote that symbolically. Let's look at the truth table for P or Q. All right, so we have to put P on the truth table. We have to put Q on there. And we have to put P or Q on the truth table. Now, make sure if I'm going too fast that you pause at different parts and copy stuff down. That's the advantage of this being on video. So let's look at the truth table. Again, the combinations for P and Q here are true, 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 false, false, true, and false, false. Okay, so P or Q. If both P and Q are true, then the entire statement is true. So if I rolled a 4 is true and I burnt my toast, then the statement I rolled a 4 or burnt my toast is also true. True, false. Well, I rolled a 4, that would be true, but I didn't burn my toast. So the entire statement is still true, right? I rolled a 4 or I burnt my toast. Well, I did roll a 4, so then the overall statement is true. Okay. To make this even simpler, if I say I rolled a 4 or I rolled a 6 and I rolled a 4, then the entire statement is true. The same thing's going to be true for if the first one's false and the second one is true. The entire statement is still true. And then, but if they're both false, then the entire statement is false. So if I didn't roll a 4 and I didn't burn my toast, then the statement I rolled a 4 or burnt my toast is not true. All right, so some examples here. Given the statements to the right, classify each of the conjunctions and disjunctions as true or false. So here we have some statements, and it's going to be helpful if we just quickly lay out which ones are true and which ones are false, okay? So 4 plus 3 equals 7, that is true. 4 plus 3 equals 6, that's false. 3 times 4 is 12, that's true. And 3 times 5 is 9, that is false. So then we can come over here and classify these conjunctions as either true or false. So let's see. We have P and Q. So I go to P and I go to Q, and I see that both P and Q are true. All right, so that means that the overall statement must be true. It might be a good idea to pause here, actually, and try all of these, and then play the video and see how you did. In fact, if Substitute is playing this video, please pause the video for my students and have them try these, give them a couple minutes, and then play the remainder of the video. All right, hopefully you paused and tried these. P and R, let's check that one out. P is true, R is false. Okay, so that means that overall it's going to be false. Because one of them is false, then the whole statement has to be false. R and S. So we check R and we check S. They're both false, so overall statement is false. Not P and Q. Okay, so let's check not P. So P is true. Not P then would be false. So I have false and true. That means overall that statement is false. Let's check this one. P and Q. I'm sorry, not P and Q. If I go to P and Q, I see true and true, but the negation of the true statement would lead to a false statement. That one's false. We come over here to do the F through J. So P or Q. So I check P, that's true. Q is true, so that's going to be overall true. P or R. True or false. So we have a statement that's true or a statement that's false, but one of them is true, and it's a disjunction, so overall it's true. R or S, okay, so both of those are false, so that means overall the statement is false. Not P or Q, okay, so let's be careful here. Not P, so P is true, but not P is false. Or Q, and Q is true. So because one of those in the disjunction is true, the whole statement has to be true. Last one here, not P or Q. So P or Q, let's check that. P or Q is true, right? True for both of them, actually. And then we've got the negation of that, which is going to be false. All right, so let's go on to the next definition here. Logically equivalent. Two statements are logically equivalent if and only if they have the same truth values, okay? So some statements will be easy to check to see whether they're logically equivalent, all right? But a truth table is really going to be the best way to figure out if it's actually, if two statements are logically equivalent. And the other thing is, you can prove that it is in fact the case with the truth table, okay? So that is a step greater, a step more evidence than just is it true are they logically equivalent or not? Can you prove that they're logically equivalent? Well, to do that, you need a truth table. Okay, so what we want to do in this example is prove, is P and Q logically equivalent to Q and P? Now, your intuition is that they're logically equivalent almost certainly, right? If I say, it rained today and Sam plays tuba, or I say, Sam plays tuba and it rained today, those feel like the same statements. Can we prove that they're logically equivalent, or those probably feel like equivalent statements? Can we prove it? So to prove this, we're going to put each part of what we're analyzing in the truth table, so P and Q. And then we're going to put P and Q, because we're checking that out, right? And then we're also going to put Q and P. Okay? So the combinations for P and Q are as they were up above, T and T, T and F, F and T, and F and F. P and Q, that's true. So P and Q with true and false, that's going to be false overall because one of them is false. This one's going to be false overall because one of them is false. This is going to be false overall because they're both false. Okay, so that's T, F, F, F. That's just what we had up above, right? Oh, I'm sorry, in this one up here. And then over here we have Q and P. Well, it's going to follow the same rules. So if they're both true, then overall the statement's true. If one is false, then the overall statement is false, so the next two are false. And then if both are false, then you have false. Now this one's not hard to show, but you can see if these were a little more complicated, the truth table would help you out. So basically what you do is you check, are these the same? Do they match? And since they do, since they match, they are logically equivalent. Okay, so we proved it. Good job, us. Okay, now, we're going to do one that's a little more complicated. Again, this would be a good one to try on your own. So use a truth table to determine whether these two statements are true, not P or not Q. Not P or not Q, and also not P and Q. Okay, so hopefully you paused it, gave it a try. Let's list out everything that we need to know. So we need to know P and Q, and not P, and not Q. And then the things that we want to check are not P or not Q. And we want to compare that to not P and Q. Okay, that's kind of not a straight line, sorry. All right, so the combinations for P and Q are true, 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 false, false, true, and false, false. And then not P, that's just going to be opposite of all these P values, right? So that's going to be false, false, true, and true. Not Q, opposite of these truth values. So that's going to be false, true, false, true. Okay, and now that we have that kind of groundwork set, we can go finish and actually compare the things that we want to compare, okay? So not P or not Q. So I'm going to check here. Not P or not Q, that's false or false. That means overall the statement is false. False or true. So the overall then the statement is true because this is an or statement. So that would be true. True or false. A statement, the first statement's true, the second one's false. One of them is true, so overall we get a true statement. And then true or true, well, that means overall the statement is true. Okay. Then we'll move on to the next one. Not P and Q. Okay, so I go over to P and Q here, so I'm looking at these two columns, and it's the negation of the and. Okay, so let's be a little careful here. So we have true and true. So the inside the parentheses would be true, but we're going to negate it, which would make it false. Okay. Then we have true and false. Remember, that makes the inside of the parentheses false, but we're going to negate it, which makes it overall true. Same thing's going to happen here. False and true, that makes it in the parentheses false, but we're negating it, so I get true. False and false, inside the parentheses is false, but we're negating it, so it's true. and then I check, are these the same? And they are. It turns out that saying that the negation of P or the negation of Q is logically equivalent to the negation of P and Q. So this is a great example of where, you know, your intuitions about whether these two things are logically equivalent or not might not help you very much, but the systematic approach can. Now, also remember that this feels very abstract, but we could easily make P and Q actual statements, right? Actual logical statements, as we did up above here. And you could figure out, you know, are the two statements logically equivalent or not, right? So that's pretty much all we have for compound statements.